So before I do an example of using the derivative definitions, I'd like to just do a quick review of the average rate of change on an interval. So if I have an interval a to x, if I wanted to find the average rate of change, I would, and I'm going to call that, right, the slope of the secant line, because the average rate of change is the slope of the secant line, right, from when we first introduced it. And I'm going to look at the change in y over the change in x, which is the definition of slope. So recall that, if you're here at a and you want to find the average velocity between a on the interval a to x, you look at the change, right, in the y, which is f of x, and this is f of a, over the change in the x, which is x minus a. So an alternative way of writing that is if we let x equal a plus h. So on an interval, that would translate to the interval a, comma a plus h. So all I did was, grab another color, is rewrite x in terms of a plus h. Okay? So on the interval a, comma a plus h, the average velocity, or the slope of the secant line now, would be f of a. X is a plus h, so I'm going to replace the x in this formula with a plus h. And, of course, f of a stays the same. Divide that by, in place of x, I'm going to put a plus h minus a. So all I did was substitute x equals a plus h into this first definition of average velocity. And I'm going to call this definition 2. So algebraically, if I simplify this is just simply f of a plus h minus f of a, and the denominator simplifies to, I'm just going to grab a different color here, a minus a is going to cancel out, so the denominator simplifies to h. So that's an alternative way of writing the average velocity. Well, what is instantaneous rate of change, right? So the instantaneous rate of change is just the limit. So I could take the limit of both of these equations and come up with the two definitions for derivative. So, and I'm going to call this the slope of the tangent line now instead of the secant line, because that's what the limit is of the average velocity, right? So for definition 1, if I take the limit as x approaches a of f of x minus f of a over x minus a, you can see what happens, right? Which is what we saw before. As x approaches a, this denominator approaches 0, so we're approaching the instantaneous rate of change. Okay, so that's for definition 1. For definition 2, the slope of the tangent line is also, again, a limit, but this time we're going to use this definition, right? So as h approaches 0, this is going to be the limit of f of a plus h minus f of a over h. And again, you can see what's happening here as well. And I'd like to do an example for both of these definitions, definition 1 and definition 2. So I think I'll just make 2 separate videos here. Well, let's see how long this video goes. So let's look at an example using definition 1. For definition 1, right, you're going to be told to use a definition to find the slope of the tangent line. So use definition 1 to find the slope of the tangent line of the function at a point, at point P. Okay, so we're given that f of x is a polynomial, and it's minus 3x squared minus 5x plus 1, and the point that you're given is 1, negative 7. This is textbook number 10. Okay, so let's use the first definition to find the slope of the tangent line at the point. So the first definition is the limit as x approaches a of f of x minus f of a divided by x minus a. Well, the point that you're given them that we're interested in, this is a, let me get another color here, this is a, and this is f of a. Okay, so this is the point a, comma, f of a. So now let's substitute into this equation the information that we have. And this is the equivalent of the limit as x approaches, a is 1, of f of x, I'm going to substitute that in a minute, minus f of a, which is a negative 7, all over x minus 1. So let's substitute now in the function. So this is the equivalent of minus 3x squared minus 5x plus 1, and then plus 7. So all that I did here was substitute in for f of x, and then I just resolved the sign. Divided by x minus 1. And I need to take the limit, erase that equal sign, as x approaches 1. Okay, let's algebraically combine the constants and see what we can do as far as handling the limit of a rational function, which you have the skill now to be able to do. This is 5x, and this would be plus 8 over x minus 1. And I can see a factoring going on here. See if I can factor this, and I do believe that I can. Up top, I can factor this into minus 3x minus 8, x minus 1, all over x minus 1. Right? Check that by foiling. Make sure you get back, and indeed, yep, first, outer, inner, last. Right? I get back. So we're good. That factors, which means this term is going to go out. Cancel out with that term, and we're left with this problem, which is very solvable, right? Minus 3x minus 8. So substitute in 1, and you get minus 3 times 1, minus 8, and the answer there is minus 11. So what is minus 11? Well, minus 11 is the slope. That's the slope. So minus 11 is the slope of the tangent line. I just want you to understand what you just saw for the slope of the tangent line at the point my 1 minus 7, right? 1 minus 7. So we found the slope, but how do we find the equation of the line, right? How do we find the equation of the tangent line to the curve, to the function at that point? Well, the equation is just like any other equation. All right, we know the slope of the equation, and the equation for the tangent line is going to be given by y minus f of a, and this should look familiar. This is just the point slope formula, x minus a. So the equation for this, the equation for this, I can't scroll anymore, that's the problem. The equation for this line is going to be y, f of a is simply negative 7. Substitute in, the tangent we found is minus 11, the slope of the tangent line at the point 1, negative 7 is minus 11, and then x minus 1. So the equation of the the tangent line to the point 1, negative 7 is just y equals negative 11x plus 4. So that's the equation of the line. And that's how we found the this slope of the tangent line using definition 1. So let's do an example using definition 2. I'm going to go to the next page. Okay, so definition 2. Let me grab a different color here. Definition number 2. I'm going to pause and find a good example here. Okay, here's the example that I chose for definition 2. It's got a little bit more algebra involved, and I think this is always a good thing to work on our algebra. So this is textbook number 22. We're going to use the definition 2 to find the slope of the tangent line of a function at a point. And the function that we're given is 1 over 2x plus 1, and the point is 0, 1. So again, this is a, and this is f of a. Okay, so let's begin by writing down the definition number 2 for the slope of the tangent line, and that's the limit as h approaches 0 of f of a plus h minus f of a over h. And this second definition moves us more towards the formal definition of a derivative. So I do want you to concentrate on the second definition. So we know what a is. A is equal to 0, and f of a is equal to 1. So let's replace in this equation what we know so far, and that's f of, excuse me here, let me write this a little differently. F of a is 0. 0 plus h minus f of a is 1 all over h. So this equation, or this limit, boils down to f of h minus 1 over h. So I'm going to substitute in h into f of x. So this becomes 1 over 2h plus 1 minus 1 all over h. Now algebraically, we need to do some cleanup here. I'm going to grab a common denominator for the numerator, and I'm left with 1 minus the quantity 2h plus 1 all over h. And continuing with the algebra here, I'm going to clean this up a little bit. This is the limit as h approaches 0, and I'm left with up top 1 minus 2h plus 1, and on the bottom h times 2h plus 1. Distribute in that negative sign up top, and you get 1 minus 2h minus 1 all over h times 2h plus 1. Okay, so I can clean this up even further, and I've got the limit as h approaches 0 of minus 2h over h times 2h plus 1. And again, I can do some canceling out of the h's, and this becomes the limit as h approaches 0 minus 2 over 2h plus 1. So now let's substitute in 0 and see what we get. This is minus 2 over, because that's how we resolve, right, limits for rational functions as long as the denominator does not equal 0. And we're left with the quantity negative 2. So that's the slope of the tangent line at the point 0, 1 for the function 1 over 2x plus 1. So let's continue down this path and find the equation just as we did with definition 1. So the equation and the formula for the equation is just the point slope formula. And we know what a is, and we know what f of a is, so this is y minus 1, and we know the slope that we just found was negative 2, x minus 0. So the equation is y minus 1 minus 2x, or simply y equals negative 2x plus 1. So that's what we found up here, just so you know what you're finding, right? That's the slope of the tangent line at the point 0, 1. And this is the equation for the tangent line. At the point 0, 1 for the function 1 over 2x plus 1. Okay, so that's what you have found in both of these cases. That ends this video.